This program is a presentation of University of California Television. Your support makes UCTV's programming possible. Contribute online at uctv.tv/support. Check out our YouTube original channel, UCTV Prime, at youtube.com/UCTV Prime. Subscribe today to get new programs every week.
Good evening, everybody. Welcome to the 7th annual Las Cumbres lecture. My name is Tommaso Treu. I'm a professor of physics at the University of California, Santa Barbara. And on behalf of the UCSB and the Museum of Natural History, I would like to introduce tonight's speakers, because we have two speakers tonight. So the first speaker will be the founder of the Las Cumbres Observatory Global Telescope Network, our partner in discovery and education, Wayne Rosie.
Hi, welcome everybody. I'm curious to ask the audience, how many people in the audience have been to all of these lectures? Not that many. How many of you have been to at least 4 or 5 of them? There we go. So there are a lot of repeat people. Just curious. Well, thanks for coming. We're pleased to do this every year. It's really sort of the high point of the year and something that happens somewhat before Memorial Day, and then our employees go scatter to Yosemite and the Sierras, and we never see them again all summer. But this year's a little different because we're deploying telescopes, and we've been engineering and designing and building for a long time. And last year I said I'd give you a brief report on what we were doing. So I'm going to try to do that. And I'm a little bit computer challenged here. It's a Macintosh, so hopefully, there we go. Get my first slide here. Basically 3 weeks ago, on about, I think, March 28th, the first 1 meter showed up at McDonald Observatory in West Texas. McDonald is in the Fort Davis Mountains. It's 3 hours from nowhere at about 6,000 feet. Actually, if you look carefully in the diagram, you'll see some telescopes behind us. That's the 88-inch and the 107-inch at McDonald. That's about at 6,800 feet. So I do commend this area. It's a great place to visit. It's beautiful desert. Here's Thursday morning. That's David Petrie, longtime Santa Barbara resident and our tech writer, and Vincent Posner guiding the telescope into our dome. That was Thursday morning. And then Saturday afternoon, we had a deadline. We were going to have first light on April 1st, UT. Well, here's a quick picture of the telescope in the dome. It has its instrumentation on it. That's the sort of gray stuff down at the bottom, the filter wheel and camera. And then the next slide is the generic sunset slide. This is the dome opened up, waiting for the sky to get dark. So we, shall we say, worked very hard. We had a rule that we would only work 10 hours a day. We kind of followed that for the first 2 days, but I think we broke it on Saturday. And now you guys get the treat, which is never before done in the history of astronomy. We're going to show you the actual first light image, the actual first photograph taken by the telescope. This is it depends. I'm quoted as saying something like, this is the accumulation of thousands of manufacturing tolerances. I hadn't had anything to drink. I probably was dehydrated to have made a statement that inane. But many of the technical staff of McDonald Observatory were watching this, and they were oohing and eyeing this. This is basically an out-of-focus image. So in some sense, we're looking at the light coming off the primary mirror. And so it looks like a donut. And if you look carefully, there's these teeny little bits of light. We call them dimples, and there's a long story behind that. But what's important about this image is the hole in the donut is almost centered. And that was kind of like the amazing thing. Most telescopes, when they're first put together, are not this accurate. So this was done by dead reckoning, and the story of how we got here was fairly sad and will never be recounted. But Vincent managed to get this thing aligned to this level, and we were all very pleased. And so then we aligned the donut and we focused the telescope. And 20-second light, which is, I asked one of the astronomers at McDonald, his very individual astronomy, what's the best object in the sky right now? And he said, NGC 22, blah. So I typed it in, went to it, and we did a 30-second exposure, and here it is. Okay, so this was an incredible thrill, probably the most thrilling image I've yet experienced in my career, just because it was like sort of in focus, and looked pretty good. And then last part of my little talk is the post-champagne picture. We opened a bottle of champagne after that. Here's the team. Annie Hellstrom, the woman in the middle, was the team leader. She kept all of us under control. Vincent over on the left, David Petrie, Annie, myself, and Bill Wren, who's the guy who told us what image to do, and Bill and I have been working together for a long time. So that's our report for this year. Our scheduled activity is to install 9 more of these this calendar year. So next year, we'll have many more first light images, and you can grade the donuts and see if we do better or not. So I thank you and have a great lecture here. It'd be neglectful for me not to say there's about 45 other people at Las Cumbres today and a peak of over 65 who made this happen. So it wasn't the 5 of us, it was everybody else. Thank you.
Great. Thanks, Wayne. We look forward for the many discoveries of these telescopes. So without further ado, let me introduce tonight's speaker, Las Cumbres lecturer, Professor John Carson. John is Professor Chandrasekhar Distinguished Professor at the University of Chicago and Deputy Director of the Kavli Institute for Cosmological Physics. John doesn't like lengthy introductions, so I will be very brief. Suffice it to say that John in his career received numerous awards for having developed technology and telescopes that changed the way we perceive the universe. Please let me introduce John Carson.
No, thank you. Thank you. Are we on? Can you hear me? So this is really quite a pleasure to be out here. Boy, when I saw the big room, I thought, well, they'll never get people to fill it. You guys are terrific. Thanks so much for coming out. And whoever arranged the weather to break, thank you very much. I could make jokes all week about Chicago weather, but I can't anymore. I'm going to talk about my research in what I love doing, which is studying the universe. You know, the universe as an evolving thing with an origin. And I do my work at the South Pole. I do my research at the South Pole. And so this is our telescope, which I'm very proud about. We'll talk more about that toward the end of the talk. But I just want to warn you, don't call it a satellite dish. I'll get a little touchy about that. It's a very precise, very accurate millimeter wavelength telescope, 10 meters at the South Pole. So I was thinking where to start, and I thought I would start here. This is an image which I hope you can see. Actually, can people see the images? We need to get the lights. There we go. Okay, this is an image of something I hope you all recognize, the Milky Way. pretty big field of view. And 100 years ago, this was an image, what people would say was an image of the universe. The universe was made out of stars. Einstein was developing his equations of general relativity and applying them to the universe. And this is the universe he applied them to. The universe was a universe of stars and very compact. I love these images. So you can pick a little spot out and zoom in, and you see these just wonderful images. Every one of these is a little star in the Milky Way, or a big star, and they're different. That said, I don't study stars at all, really. And about 80 years ago, Edwin Hubble identified this object, which had been a debate. What were these objects, these smudges in the sky? He identified it correctly because he could recognize some very, very dim stars in it, but recognized they were, in fact, very, very luminous stars. And he correctly placed that this was another galaxy. And of course, our idea of the universe grew immensely. There were other island universes or galaxies, each with very, very many stars. And as you know, we now think of the universe as a universe of galaxies. And not only that, the universe of galaxies which are dominated by dark matter. So since this time, of course, optical astronomy has done very well. And we just heard of this tremendous future of the LCO doing transient time astrometry and optical astronomy. But people haven't just looked at galaxies. This is, by the way, M31. It's the closest big galaxy, similar to our Milky Way. And we're actually going to collide with M31. We're going to completely redistribute the stars into galaxies, probably build some big galaxy in about 4 or 5 billion years. You don't have to worry about that. The sun's going to burn out around that time, too. But this thing, you look at it, it subtends an angle about the size of your hand stretched out, right? It's a big thing on the sky. And these days, using automated telescopes, people have surveyed huge, vast parts of the sky, at least in area. And I'm going to show you a movie, we'll see if it works, of going through, is it moving? Yeah, it is moving. This is the Sloan, coming from the Sloan Digital Sky Survey, where, of course, they can't really fly through the universe, but they mapped over about a fifth of the whole sky, 8,000 square degrees, all the galaxies, figure out their distance or approximate distance, and then put together this movie of what it might be like to fly through. Now, of course, these galaxies are very big. If you were going this fast, you would be violating Einstein's speed of light. But the thing I like to show, and actually they do this if you ever get a chance to do it in 3D, and it's really, really fun. But, they're not just uniform. They kind of clump up. There's filaments of galaxies. You'll see flying through some groups of galaxies and then some voids of galaxies. And we think now the universe as this, universe of galaxies. Each galaxy has many, many stars. And I think we'll see maybe some groups coming up at some point. Like here's a cluster of galaxies, and they're going to be prominent and be very important later in the talk, these clusters of galaxies. Anyway, let's go now to another image. And probably many of you have seen this. Is the deepest optical image, looking as far away as we can into space. And this image subtends an angle about the size of your pinky at the end of your arm. So this is just a tiny little, looking out at space, tiny little piece of space. Yet everything you see in here, every little blip, yellow light, every little blip is a galaxy, right? So you can imagine, you could count these up, say, well, how many of my little fingers would cover the whole sky? And you could figure out how many galaxies are in the observable universe. And I use that term very specifically, observable universe. We can't observe the entire universe. It's too far away, but we'll come to that story later. So I want to give you a number to remember, right? So you only have to remember one number tonight. It's 100 billion. So what is that, 100 billion? Well, it's the number of stars roughly in the Milky Way or in Andromeda galaxy. A big galaxy like ours has about 100 billion stars. It's a big number, it's a lot of stars. But if you do that exercise I just told you about, count the galaxies you can see in that very deep image, and say, well, how many are over the whole sky? It's about 100 billion galaxies. Then if you can measure, a little bit more about the universe, and we'll talk about this briefly, it's the age of the universe. Almost. It turns out you have to do it in dog years. The universe is 14 billion years old. But you can remember dogs, you can remember 100 billion, and figure it out. You do the arithmetic later. It's also about half So it's a very big number. But you know, when you see what's happening in Washington, it starts to seem like a small number again. Here's the most interesting, from my viewpoint, the most interesting observation of this image, this deepest ever image, and that is it's mostly black. It's mostly not filled with light. You pick a point and you look real deep, you're not going to see a galaxy, you're going to see black, right? That's very interesting. And why is that interesting? Because what are you seeing if you're seeing black? There's no galaxy there. You're seeing past the galaxies to a time, and I mean that right, past to a time before galaxies formed. Right? So if that all makes perfect sense for you, then you can sleep for a little while. But light takes time to travel. So when you see farther away, you're seeing back farther in time. And so you're actually seeing to a time, you're not seeing anything there yet, but you're seeing to a time before galaxies formed. So the sky is really quite black to our eyes. If your eyes were a little bit bigger, like a lot bigger, and everything scaled up so you could see millimeter or microwave light, you wouldn't see this. The sky is actually very, very bright. In fact, there's a lot of, in fact, it's very bright in the microwaves. And in every direction, it's bright, right? And that brightness was discovered in 1965 by these two guys, Arno Penzias and Bob Wilson, using this funny-looking telescope. And what they were looking for, they wanted to do radio astronomy. It was kind of a new thing, but they built this thing. They were supposed to also find out what is that what's that noise that's affecting transatlantic communications using microwaves. And so they built a very sensitive receiver. That's the name of the game always, build very sensitive instrumentation. And got in here, and then they found there was all this noise. It was a lot of noise, light, essentially, but microwaves. And they spent years riding around, doing every test, cleaning the bird debris out of here, figuring out what the heck could it be, and finally concluded it was cosmic. It was cosmic and orange and coming from every direction. And when they went public with this observation, of course, the people who had been working in the early universe realized right away they discovered the cosmic microwave background. They discovered the light coming from the very early universe, and I'll describe that in a minute. It was a tremendous evidence for the Big Bang. They won the Nobel Prize, 1978. In fact, this is them going back. They didn't actually dress like that to work. This is back, poised in 1978. And I always like to say a couple things when I see this picture. I mean, it's a tremendous watershed event, but it shows two things. One, that all cosmic microwave background telescopes are weird looking, and half of all cosmologists are bald. So what could be causing this radiation, right? I mean, the theorists had it. And there's another observation. This was about 80 years ago, about 10 years, about 80 years, 1930, when Edwin Hubble again and his collaborators using the Mount Wilson telescope discovered when they looked at these galaxies, these bright galaxies, they had discovered this nebula, other island-like the universes. The farther away they were, they did spectroscopy, they could look at the hydrogen lines, and they could see the lines were displaced in wavelength. And what causes that is if the object appears to be moving away from you, is moving away from you, that would cause it. And so they could plot the velocity, how far away these things were with this axis, and they didn't do that very well. They just said they looked farther away. They got off by a factor of a few, but this they got very accurate, the velocity, because they could do very accurate spectroscopy. And they noticed that the farther away you looked, the faster things were moving away from you. That the universe, as measured through the galaxies in it, was expanding. And so there's this very famous picture here of Albert Einstein. Remember, Einstein's universe was this universe of the stars. When he applied his equations, his famous equations of general relativity to the universe, it was the universe of stars. They weren't moving away. But his equations said the universe would not be stable. He had to add a fudge factor. It's like he had, the answer in the back of the book was the stars aren't moving, so he had to add a little correction. He called it his cosmological constant, Einstein's cosmological constant. And it acted like a repulsive force, stabilized the universe from all collapsing from all the gravity, right? Brilliant, brilliant thing to do. But in fact, the universe is not static. It's expanding, and so he called that his biggest blunder. I always like to show this picture because, you know, Einstein's a very famous theorist. I'm an experimentalist. I build things and that. So you know he's not really looking through there. And there's Edwin Hubble, who's very anxious, seeing someone as an instrument. But Edwin Hubble would never smoke a pipe near his delicate instrument. So this is poised, I'm sure. Anyway, do this experiment sometime so you can really understand. When we say expanding universe, we don't mean that we have galaxies flying through space. In fact, we can prove today, and the kind of observations to talk about later, maybe after the lecture I could tell you, we can prove that that's not the case, that the galaxies are all stationary, for the most part, you know, moving a little, but they're stationary relative to the space. And it's the space itself that's expanding. And that theme will come up a few times. So you can take, this is just a little fun exercise. You can, on a computer or on a piece of paper, draw some galaxies. And then don't move the galaxies. Just expand, stretch the piece of paper out. All right? So just stretch it out. I'm going to stretch it out 10%. Right? Do it again. And say that's the universe 2 times later. 1 time step and another time step. But I didn't move the galaxies relative to each other. I just expanded the space. Then, of course, we're here in the middle. Right? That's what everyone believes. And if you say, what does it look like from us? Well, the guys next to us have barely moved, and the guys very far away from us, they're really moving fast. That's how it appears to us. You get that Hubble flow. And then you say, oh, but but the universe started there. And you say, well, no, it could be anywhere. Right? Whoops, went the wrong direction. If you pick that guy to stack them up, what do they see? The exact same thing. Right? You pick anyone you want, stack them there, because of course if you're on a galaxy, you're always there. That's your vantage point. And you see this expanding universe. Right? So the way we explain it is not there's a big explosion, everything's flying through space. Space itself is expanding. Right? And the amazing thing is we can show that to be the case. Anyway, now think back. I want to go back to the cosmic microwave background. If you think of the universe being looking back in time, you're seeing it when it was denser and denser and denser as you look back in time. And so all the light that we see in the universe, well, its wavelengths are shrinking with the space. That means the light has more energy. The density of matter, it's getting more compressed. The energy density is getting higher and higher. And so you get to a point where galaxies haven't formed. You get to a point, going back in time, it's dense enough, stars haven't formed. In fact, you get to a point where atoms haven't formed. And if they do form, if you have hydrogen, electron and a proton get together and form hydrogen, nice little bound hydrogen, the light has so much energy it breaks it apart. It's just a plasma, right? How far back? You have to go about almost 14 billion years, 13.7 billion years back. At that time, you say, well, this is getting complicated. No, we're making things simpler. At that time, the universe is very simple. There's no stars, there's no life, it's just a gas. And that gas, here's my carefully photographed picture of the gas. You have photons. Photons, we always say that's light. Photons, light particles, are jiggling around. The electrons, they're not bound to protons. It's all ionized. It's just an ionized plasma. And there's dark matter, but you can't see it. It's dark. So if you have this plasma, well, there's a few things. One, the light can't travel very far. If it starts to travel, it sees an electron, and it bounces and ricochets off. It reflects. Now, you all know this, right? If you take a bunch of electrons and put them in like a 2-dimensional plane and look at it, you see yourself. That's a mirror, right? The electrons are free to move in that plane. It just reflects light. But take those electrons and put them in a gas, and the light will just bounce around, right? Like looking into a plasma. So if you wanted to look in this plasma in the early universe, you wouldn't be able to see the tip of your nose. It would just glow, all the light. And then you die a few minutes later. So the other thing that's important is if you take this plasma, and if there's some dark matter or some matter we don't see, it's trying to pull it in and compress it. As you compress it, then all the density goes up and the number of collisions go up. Things hit each other more often. Well, the photons, every time they hit, they push it apart. So the pressure goes up. So if you take this and you try to compress it, the next thing that happens when you let go is it bounces back. And it oscillates. That's just sound. It just supports sound waves. And if you have some dark matter, something trying to pull it in with gravity, this stuff will oscillate on it. Just sound waves. So it's easy. We just have sound waves. So what does it look like now? That was the early universe. Let's put the clock all the way back to today. You are here. You're looking out. You're going to look out. You're going to pick the right wavelengths, which happen to be the microwaves. And you see all the way out nothing until you get far enough back where you see this time in the universe when the light was scattering, when it was all ionized. So the analogy is that it's like looking at the sun. You look at the sun, there's no surface of the sun, you can't stand on the sun, but what you see is when the light last scattered. You see the light when it came off the sun, right? That photon, that particle of light may have originated deep in the core of the sun, but it just bounced around from all the free electrons until it got to the surface, then it's free to go. Right? That's how the universe was. As soon as the atoms formed, the universe cooled enough and the atoms formed, the electrons aren't free to move anymore. I mean, there's a lot of stuff in this air. Thank God we can breathe between you and me, but you see me fine, you can see the screen, because all the electrons are tied up in atoms and molecules. They're not free to interact with the light that's going around. So the universe became transparent when it cooled enough and the atoms formed. Right? So the universe is cooling, the light wavelengths are stretching out, get to a point it can't keep ionized, it can't keep the hydrogen ionized, and we see this surface. So it's like an inside-out sun with a radius and how long the light would take to get to the middle from the edge, presently 14 billion years. Right? So these telescopes are time machines, and we're inside of a glowing, inside-out sun. Right? That's what it was. That's what they saw. That's what was so exciting about their discovery. And, it had huge impact. It was the end of steady-state models for the universe. I mean, a few people might have, that was the end. Big Bang, hot Big Bang, just explained it beautifully. And, of course, the neat thing is it set off this, if we can take a nice image and see what's there, we're seeing our universe as it was in its infancy. Let's go measure that. What does it look like? And I'll show you what it looks like today. But this is an interesting story because, in fact, there was the thought, we should go and we could see the structures which seeded all the wonderful structure in the universe. They should be there. The denser regions will be a little hotter, a little brighter. Let's go look. And it should be at a few percent, right? Nothing was discovered with people trying for almost 30 years. And the reason why is it wasn't a few percent. It was at a level of 10 to the minus 5, a part in 100,000. Small variation, very difficult to detect. Easy to detect the radiation. It was detected because what is that excess noise? But it was so uniform that it was very hard to ever detect any structure. So I'll show you some of that. That was done in 1992. And I'll just throw away, that led to this crazy theory, which eventually you may believe, called inflation, which is a theory for the origin of the Big Bang. And the fact that this is smooth, so uniform, led to that theory. So let me go through some of these discoveries. So this is if you took that photosphere, that whole sphere surrounding you, and patched it onto a screen, so it would look like that, like taking the whole Earth and putting it onto a screen. That's the whole sky. It's just bright and looks like that. But if you remove the intensity of the uniform part, this was done by the COBE satellite, but there was also even early South Pole experiments that started to see this anisotropy. If you remove, as best we can, emission from the galaxy, but in particular remove the intensity, just look at the variation, this is what the COBE satellite saw. After 30 years, they finally saw it. And it's the COBE satellite didn't have the best, resolution, 7-degree resolution, that's pretty coarse, but they could see this, and it was, remarkable. So these guys, they measured the spectrum, they measured other things, and the team leaders, John Mather and George Smoot, received the Nobel Prize for this work in 2006. So let me just kind of recap. So we have, if you think of the universe now as evolving, We start out, I'll just show a picture of a piece of the universe, the cosmic microwave background. We remove, so you can see the variation. I'll remove the uniform part, just leave you with the small fluctuations. That's what it looked like as far back as we could see, shortly after the Big Bang. Then we had structure forming. The dark matter, which starts out with this kind of structure, through gravity is forming, and it forms these filaments and these structures, right? That's gravity at work on very large scales. And then what we see today is all these galaxies. There's like that Hubble deep field. And these galaxies, as we flew through that Sloan survey, they're actually look like that. They're in these kind of filaments. There's clusters, a lot of them, where these filaments meet. That kind of cosmic web is what's observed today, right? So we could say, what is this in terms of people's lifetime? So we start here. This is, let's say that someone just retired. Then this would be, the development years, the first few years where the gravity really kicked in after the photons stopped supporting things. And these pictures we can look at of the cosmic microwave background is like seeing the very first baby pictures of the universe. Right. So let me get back to this issue, which I keep bringing up, the smoothness problem, right? So, as I said, that's what the universe, really looks like. But let's get rid of the uniform intensity. Just look at the variations. They're uniform to a part in 10 to the 5. And so Alan Guth, who was the inventor of the inflation model, or discoverer, depending on your point of view, always likes to give this example. Let's suppose you're taking a nice walk, along the beach or in the hills here, and you pick up a rock, and that rock looks spherical, and it's beautifully polished like a ball bearing, right? Just like a well polished ball bearing. That is how smooth this is. That's about a part in 10 to the 5. Your thought probably is not going to be, well, I was just lucky that stone happened to be very round. You would think it was made, right? Some machine, there was some causal process which led to that being so remarkably smooth. So why is this so smooth? And you could say, well, it came from the early universe, it was all connected, but how could that possibly be? You look at this thing, you look at light, let's say, coming from that direction, and you're going to measure its intensity and its spectrum. You're going to measure everything you can about the radiation coming from that direction. It's taken 14 billion years to reach you. Then you say, oh, I'm going to look from that direction, and you measure all the light and radiation from that direction, from the cosmic microwave background, and they're the same intensity, same spectrum, same, what we would call temperature, and yet those two parts of the universe, traveling at the speed of light, have only been able to communicate with you halfway in between. How did they ever know to sync up? If you guys all came in here and you're all wearing funny white hats, with Go John written on it, I would think that you guys got together ahead of time, that it wasn't just an accident. Somehow this whole thing got synchronized, right? That's the smoothness problem. And the solution is really easy, right? You just go in the first 10 to the minus 35 seconds of the universe or so, first instance of the universe, you just stretch out space by a lot. Maybe 10 to the 60 times or something like that. That'll do it. And how does that do it? Well, you imagine you crumpled up a piece of paper and then you've stretched it out, not once, twice, but huge number. Any point on that paper you looked at then would look very, very smooth, right? Very, very uniform, right? But that paper would be, it would take light, traveling at the speed of light, more than the age of the universe to go across it. So inflation says, this theory of inflation says that you have, in the very early universe, that extremely high energy in some, this is a kind of trick thing, in some pre-existing piece of space-time, but on a Planck scale, on the quantum mechanical scale, you get this fluke high energy state, metastable. According to Einstein's equation, you will drive exponential expansion. You say, but that can't be. You're going to take stuff and whisk it out to distances much farther than light could have traveled at the age of the universe. You're going to make it huge, right? And then much later, these things can send, through light, communicate with each other. like things like that light now is only reaching us halfway. So you might say, well, that's, you forgot, John, you can't go faster than the speed of light. You can't use Einstein's equation to explain something going faster than the speed of light, because one of his postulates is nothingness. Einstein never said space can't expand faster than the speed of light. He said you can't communicate or send a signal through space. You can't send a perturbation in space that will go faster than the speed of light. But it's Einstein's equations, actually, which give you this ability and tell you that space itself can expand. That's what Alan Guth really discovered. So that's inflation, right? It might sound crazy. It solves a lot of problems, and we're trying to, every test we put to it, it passes, and we're trying to put more and more stringent tests. One test, and this is the first big test that it passed, that if inflation is right, remember I gave you that example with the paper being crumpled up, if inflation is right, then if we try to measure space-time, the geometry of space-time, it should be Euclidean. Light rays should be that. Space-time should be very, the jargon we use is flat. Not flat like, a pancake, but that light ray shouldn't curve, right? Or inflation should lead to a flat universe. So how can we check that? Well, imagine you're at the South Pole. We like to put the South Pole on the top. And you want to measure the Earth. Is the Earth flat? You're going to ask that question. So you take your graduate students, and you say, go 300 miles out, take a left turn, make a perfect right angle, go 400 miles, and then just come home and measure all the angles, right? And, oops, yeah. So right away, you know there's something fishy going on, because there's a right angle, here's a right angle, and yet you meet. So the sum of the angles add up to more than 180. You probably remember that's bad. Or if you like Pythagorean's theorem, 3 squared, 4 squared, that's not 5, that's 4 again. Right? So you say, oh, don't worry, the Earth's not flat. And you use this information and you calculate the radius of the Earth. But then, you go to bed. When you're in bed, inflation strikes. And I don't mean mild inflation. And it expands, and it expands, and it expands, and it expands by the number of times the universe has expanded. You wake up the next morning, you think, I'm not sure we did the measurements right, and you send your students out, and they get, it's perfect. It's perfect. You send them as far as they go. They could be traveling for the 14 billion years and measure the triangle, and it's flat. And as far, the age of the universe, like as far as you could see, it's flat. Right? It's very hard to have a theory like inflation say it's going to be sort of curved. It's driven flat. So we want to measure, is the universe flat? Right? And this is what supposedly inflation did to the universe. Now before I tell you how we do that, let me just say, if you like what inflation says, and I think this is very cool, it says that when you look at this map, this image of the baby picture of our universe, and you see these slightly more intense and less intense, hotter and colder spots, what you're seeing is subatomic quantum mechanical fuzz that has been stretched out to the largest structures in the universe. So you say, what does quantum mechanics look like? That's what it looks like. It's just an amazing thought. So I'm going to show you some pictures which are from an undergraduate textbook on how you can measure. Of course, it's a pretty new textbook, but how can you actually check this? And the answer is in the cosmic microwave background, but not in that map I showed you. That map I showed you is 7 degrees resolution. That's almost as big as your hand, the spots on the sky. And at the time, when you see the cosmic microwave background, at that almost 14 billion years ago, that angular scale is much bigger than light could have traveled at that time. We call that super horizon, bigger than the horizon. So you can't see structure growing because you're not looking in the right scales. You've got to get higher resolution. But if you could have higher resolution, then you can do this experiment. You could say, well, what are the structures that could grow that are within the horizon? What do they look like? And if they look like, and you can actually calculate from first principle how big they are, in kilometers, or whatever, your farlongs, whatever unit you'd like. And then how do they look? Well, if they look real big, it's because maybe they're this big, but light that you see is bending, right? So they look bigger, right? And this is what would be called a closed universe. The geometry would be closed. If it's just Euclidean or what we would call flat geometry in the mathematical term, you know, you can calculate what they'll look like. And if they're open or, you know, this kind of funny saddle universe will look like this. So we and a couple of other groups set out to do this at that time. This is the first telescope I worked at the South Pole called DAISY, sitting there. It fulfills the promise of all telescopes looking weird, but you can't tell if half the people are bald, all our hats on. We went to the South Pole, and you say, well, why the South Pole, right? Well, one is, we're looking at microwaves. How do you heat up your cup of water? If you're going to make tea, you put it in a microwave oven, right? The water and water vapor, it reacts and absorbs water very, very strongly. So we want to look at microwaves. We want to look where there's very little water in the atmosphere. Turns out the South Pole is the driest desert on Earth, or the middle of Antarctica. Not necessarily the South Pole, but the South Pole is very good. It's very stable. The sun goes behind, and the atmosphere gets very, very stable. So it's very, very good. It's actually quite high. The pressure altitude is usually around 11,000 feet. And that's because this ice and snow you see is 2 miles thick, right? There's a continent under there. It's not like the North Pole. And so you're up high. That helps you above a lot of atmosphere. The sun goes below the horizon, just gets out of the way. It's a very bright source of microwaves for 6 months, so that's not a problem. And then lastly, and this turns out to be very important for all the work I'm going to be telling you, is that you could stare at a point out in the sky, some object, and you can stare at that object 24 hours a day, 7 days a week, all year round. It doesn't move. The only thing that moves is the Earth spins under your feet. So you need a good bearing, but that's it. The sources don't rise or set, which means you can never look it to the north, but that's okay. We don't need to look at the whole universe, just a good size of a good sample. That allows you to do very deep, long observations. And then lastly, and most importantly, there's excellent support. The National Science Foundation has a research station there. They know how to work there, and you can actually carry it off. So I'll show you some results from DAISY quickly. I like to show this. This is sunset there with a time lapse every half hour or so, taking a picture of the sunset. It's kind of neat. You guys, you're in Santa Barbara, and you all hear about the green flash. How many people have ever seen the green flash? Yeah. Well, here you see the green flash, and you can say, wait a second, I'm going to go get my camera. And then come back. I couldn't find the picture. I have pictures of it. It's amazing. So these are images, now with DAISY, much higher resolution, of little patches of the sky, but put together on one page. And we always use this false color, so hotter or cooler or more intense or less intense. And you look at these and you could say, well, I can pick out a size scale. That size scale is actually the universe. The resolution of the instrument is much higher than what you see. That's what the universe is doing. There's actually a couple experiments, but another one that was in a balloon circumnavigating Antarctica called Boomerang. There it is with Mount Erebus in the background, taking data as well. And so in the same textbook, Freeman, the Universe, they say, okay, which one is right? So this is the closed or the Euclidean. Inflation says it better be this, or you got a terrible theory. Inflation's a terrible theory, or this. And it wasn't DAISY. I was hoping it'd be DAISY, but it's Boomerang, and it's this one. You can, by eye, see that. Now, I'm going to show you in a little bit that we don't just hold up maps by eye and do our theory that way, but you can see that that's the case. The universe is, in fact, as best we can tell, the geometry of the universe is flat or Euclidean. So one thing right away, Einstein also taught us that if you know the curvature of space, you know matter. Matter curves space, and that's how gravity works. So since we measured the curvature, we know the density. And it turns out the density is equal to about 3, the equivalent, it doesn't have to be hydrogen atoms, but equivalent mass energy density, 3 hydrogen atoms per cubic meter. Now I wish I could achieve such a good vacuum. That's remarkable. That's below any vacuum that's ever been achieved in a laboratory, because the density in this room right now is something like that. I always forget how many zeros, but you take Avogadro's number and go up from there. It's huge, and that's a good thing, because without that, we would have a hard time breathing. So the universe is not terribly dense overall, but in fact, it adds up, right? There's a lot of cubic meters, and it adds up. So let me go back to those maps and show you how we really analyze them. And the way we do that is we do the equivalent of like a graphic equalizer. So you're all used to listening to music and seeing some display. In fact, I know you're used to it because you all have one of these things. But so this is bass or long wavelengths, in the treble, short wavelengths, and you have some spectrum of the sound. You can measure how much bass there is, power in the bass versus treble. And what that's telling you, whoops, I'm sorry. What that's telling you, it's a spectrum of sound, and we can do a similar thing. It doesn't have to be that you're looking at some waveform changing in time. That's what sound is. You could look at some pattern versus space and analyze it the same way. And you're saying, well, how much power does it have on long wavelengths, spatial wavelengths now? How many on short wavelengths? And that's called a power spectrum. And like I said, this is, you're used to this concept. And the reason I want to explain it is because that's how we display our data. Theorists can't tell you exactly what it's going to be in the sky, but they can tell you how much long wavelength or short wavelength. And so this is the New York Times when we had the DAISY results out. And actually it was kind of nice, right above on the front page, above the fold. And then they sent you back to this page. And on that page, they had what we call, this power space, or spherical harmonic transformance. It's really like a graphic equalizer. So they assume that everyone knows and is familiar with these things, and that's how we all think in this pattern. But they're pretty sophisticated in New York. But anyway, so the idea is that this is the universe. This is the sound of the early universe. It's not just noisy. It's got a fundamental tone. It has a harmonic, and then it has what looks like another harmonic. So what the heck is that, right? Why would that be all synchronized? Well, it turns out if there's inflation and you've whisked everything out of the horizon, you start everything with very exact initial conditions, you let it go, and then the universe becomes transparent all at once. In other words, if you have inflation or a mechanism like inflation, you get this. That's exactly what you get. Not only that, and of course the location of this peak, that was just telling you that the universe is flat, which also is good with inflation. But not only that, we're seeing sound waves. And if you're measuring the sound waves and you know what's driving them, well, the dark matter. What's causing them to oscillate? Well, that's all the light pushing on the electrons back. You can solve, by looking at this, you can solve how much of that stuff you have. How much dark matter, how much baryons, how much photons or electrons, ordinary matter. And when you do that, you can put together, the pie chart. What is in our universe? And the first big surprise, maybe, is that everything we know about, everything you can find in your textbooks, everything you were taught in school, everything that physicists still know about, is in this little sliver here, 4.5%. That's it. You name something that, the chair, the protons, it all fits in there. The dark matter, the stuff that astronomers have been telling people about for 80 years now, almost 80 years, in saying that, there's something holding galaxies from flying apart, is in fact seen in the early universe, right? And it's with the same ratio. The big surprise is that when you add these together, they don't add up to the whole pie. But let me say a little bit about the dark matter too, is that if the dark matter was just failed stars or a bunch of cold planets or ordinary matter that for some reason wasn't glowing, we wouldn't see it here. This tells us that dark matter is a new form of matter. And since these kind of observations, particularly since these observations were made, people are very earnestly looking now for these new particles of matter. But the big surprise here is that, what the heck is that? And so we call it dark energy. Dark energy, well, it sounds kind of like dark matter, but it's not matter. It's not pulling things in together. In fact, we used a very, very sophisticated mathematical technique to derive it. We know the whole sum, right? Remember, the equivalent on average of 3 protons per cubic meter, and we know what these are. So we used mathematics, a trick called subtraction, and we found out that that's what's left, and we call it dark energy. And it fits our models. We have models for it. One model could be Einstein's cosmological constant. At the same time, actually about a year earlier than these measurements, there was this remarkable finding, which we probably all have heard about, looking at distant supernova. They were dimmer than they thought they should be. And what they found, and actually, by the way, this is a real image. That's not an artist's conception of a supernova going off in this galaxy. What they found was the universe not only is expanding, and even though they were looking to see how fast is the universe slowing down, what they found is it's accelerating. The expansion is accelerating. Right? It's remarkable. And they actually got the Nobel Prize for this year, just a few months ago. So they have this in their first paper, maybe it was the first paper, but it's Science, with Einstein looking perplexed and maybe a little happy, because the leading explanation for this dark energy, this cause of a force causing the universe expansion to accelerate, there's acceleration, there's a force, is Einstein's cosmological constant. Well, that's pretty odd. So, what the heck is dark energy? That's what we want to know, and we want to be able to test it. And that's what I'm finally getting to our experiment at the South Pole. So here's the thing. We know there's dark energy. We know from supernova. We know from those observations. Theorists say, well, if it's Einstein's cosmological constant, in modern day, what that would mean in modern day language of physicists is it's the energy density of the vacuum. Empty space has energy. So let's calculate it. We know those virtual particles can come and annihilate. We know quantum mechanics. Let's calculate that. When they do that, they're off by more zeros than I've put on any one of these charts. They're off by 120 orders of magnitude. Now, to be fair, they claim, don't trust these calculations. We don't quite know how to do it. So they're perplexed. We know it's there. Let's go measure things. I'm an experimentalist. Let's go see if we can measure things. So when you think about what the supernova teams and some other similar teams, they're measuring geometry. They're measuring the acceleration of space. Maybe what's wrong, maybe it's not the cosmological constant. Maybe general relativity is wrong. Maybe our theory of gravity is still incomplete on large scales. So another way we can try to measure this is, given a theory for dark energy, you make very definite predictions for how structure will grow in the universe. So we have an idea of, let's go measure the biggest things that the universe has managed to produce and see when they grew, how they've grown, and try to put together a history there and see if it's consistent. So one of the things that's kind of interesting is that this is, you've seen this many times now, dark energy, dark matter, and everything else. That's today. But if you're going to say, what was it like when we see the CMB? Well, if Einstein's right, and its cosmological constant is just the energy density of space, well, there was less space then. There's about 1 billion times less space. And the density of things like matter went up 1 billion times. So if we say, what did that pie chart, if we made it then, look like? It would be like this. You wouldn't even find dark energy on it, right? So there's very strong evolution in the universe driven by dark energy, and that's what we want to look for. So if you don't like pie charts, here's another way to look at it. Early in the universe, dark matter is king, and through gravity, it's just pulling things together, and thank God, right? I mean, there's structures, there's magnificent stuff, there's the stars formed, we have the elements, heavier elements made us, thank God for dark energy. And in fact, dark matter. Dark energy here would be in the very early universe, not less than a dot on the page. But as time goes on, the dark matter is being diluted. But dark energy, if it's a property of space, it's just happy to sit there and do its thing. And today, it's about 2 or 3 to 1. It dominates. And tomorrow, it just takes over. The universe is expanding like crazy, and cosmologists in the distant future are going to have to rely on these old books or whatever, find an old Kindle, and see that, in fact, there were galaxies. There were, because they will be whisked. The expansion will be going so far they won't be able to see the nearby galaxies. They'll be pushed out beyond our horizon again. So, seems totally crazy, right? But that's what it's telling us. We want to measure this. Could this actually be right? And that's what we want to do with the South Pole Telescope. So I know I'm asking you to make a lot of connections here, but I only have one more, and then we'll take a nice little travel log. So here's the next one. The largest things in the universe that have formed. When I mean like formed, be bound together. The Earth is bound to the sun. The moon is bound to the Earth. The sun is part of this gravitationally bound system, the galaxy. And then the next largest thing, which is the largest that the universe has managed to do, are called clusters of galaxies. They're wonderful objects, and this is one. In fact, this thing you see in the background is that there's so much matter in here. There's so much curved space from, local to this galaxy cluster from dark matter, that this is a background galaxy, the same one that you're seeing the light being bent around. Right? They're very massive objects. And what we want to do is basically find them, when did they form, and put together this cosmic history of the tug of war, kind of like that cartoon I showed you, of dark energy, dark matter, battling it. How did they evolve? Right? The problem is that these, while these are the largest things, they're very rare, and they're hard to find, especially distant ones. And you can't just say, I found one. You have to find them all. And I'm going to show you how we did that. Let me show you, let's see if this works. Just to give you a sense, this is another one of these structure formation things. So here the white particles, those are showing a certain amount of mass in dark matter. And in the middle here, this is going from 20 million years after the Big Bang to today. And it's forming, you'll see that things light up, it's forming a galaxy cluster. It's a simulation doing that. It's 3D, it looks great. I hear it's looking a little washed out. But you can see that the stuff is coming in, you can see some galaxies starting to come in, and it's taking the age of the universe to do this. Right? And that's why there's no bigger class of objects, because there hasn't been enough time. But of course, with dark energy kicking in, it doesn't matter. The big things aren't going to form anyway. So there's this thing forming here, and that is going to be a galaxy cluster. And you can see it's lighting up. It's getting bigger and bigger and bigger. But it's taking, very slowly from those very subtle things in the beginning. Over a lifetime of the universe, or age of the universe, you form it. So here's a picture of one, another one, and you can see, sometimes the most massive ones are thousands of galaxies, have these arcs showing that there's background galaxies being distorted by the mass. It turns out the light you see, it's a couple % of the mass. The galaxies, we obviously call them clusters of galaxies because, look, it's beautiful. But the galaxies themselves are trace particles. Most of the ordinary matter is in this very hot gas that fills up the things. And it's so hot, because it's fallen to this tremendous amount of gravity, it glows in X-rays. And at these temperatures, even iron is ionized. So you might say, so let's not look for the galaxies. They're hard to find. They're hard to, so many galaxies. Can we look for this? And the answer is yes. You can look for the X-ray gas, but X-ray telescopes are very expensive. And as they get farther away, these things get dimmer. And so it's very tough, very, very hard to find them. And we don't have a telescope that can do that efficiently. But here's another way. And the trick is that the amount of gas that leads to this emission is about an order of magnitude more than the amount of stuff that's in all the galaxies. This is the dominant reservoir of the ordinary matter. And so if you think of that, I told you about if you have light and it sees electrons, it rattles around and it ricochets and scatters. So imagine you have a lowly, background photon in the microwaves, and it's coming across and it sees this big reservoir of plasma, very hot gas, all that free electrons. Well, what will happen is, it'll go right through. But every now and then, about 1% of the time, it'll scatter. So it's a subtle effect. And when it scatters, these are really hot electrons. It tends to scatter to high energies. And so when you're looking in the microwaves, it's gone. That photon is gone. You see fewer photons. The microwave radiation. When you look towards the cluster of galaxies, towards the background, you should see a hole in the sky, a shadow. Right? And the cool thing about that is if you can detect it, the depth of that shadow doesn't matter where that galaxy cluster is. It could be on the other side of the observable universe. It could be right next door. You'll see the same shadow. So this would be a great way to go find all these clusters and put together over cosmic time the tug-of-war between dark energy and dark matter. So now we're to the telescope. We're going to do this, right? We're going to build this. We're going to find them all. We're going to see is dark energy consistent with what Einstein had? Is general relativity appear to be right? So here's our telescope. I'll say a little bit more about it. It was designed for this experiment. It's 10 meters across because we have to be able to see these galaxy clusters. We have to have the resolution. 10 meters of microwave is about like your eye to visible light. It turns out we have about the same resolution as your eye. It's about an arc minute. Very big field of view. It's very clean. That is, the rays come down, very precise mirror, a 20 micron arm surface over 10 meters, and in here to the receiver, which I'll show you in a bit. We have to build our own detectors. You can't buy these. There's unfortunately, no commercial market, but we enjoy doing that. We cool them to minus 459 degrees Fahrenheit, or a quarter of a degree above absolute zero, to get very, very sensitive measurements. But let me show you how we get there and how we built this thing, so you can relax for a little bit. And I've been making you think hard. You get to New Zealand. You go through the United States Antarctic program. It's funded by you through the National Science Foundation. You get to fly on one of these things if you're lucky. This is the C-17 Globemaster. And as you can see, it doesn't really have a lot of windows or anything, but it's a powerful jet. Your cargo, every seat is an aisle seat, but there are no window seats. And there's our cargo. We have all our gear. There's just a little window. You can see one in the door. Those are so the load masters can look at the engines to make sure there's not something going wrong. But we like those little windows. You fly down to Antarctica. This is a picture out of one of those little windows, getting close to an island out there. You land then on sea ice. This is the ice outside the Ross Sea. And you can see people now with their gear there. You go to McMurdo Station. So this is the United States Antarctic Program's main station on Ross Island. That's pretty much the farthest south you can get in with water access in Antarctica. It looks pretty scuzzy. It's not so nice. But when you're here looking out, the scenery is spectacular. It's really amazing. But this is, it's a depot. An interesting thing is there's McMurdo here. This is Scott's hut. So Scott's hut where he went, this is the 100th year centennial of the first people going to the South Pole. And Scott and his men stayed in this hut the year before, and his men stayed. It's still there. You can actually go in. It's remarkably well preserved. Apparently the condition this is in with pieces of wood missing is because they were burning the wood, not because, no one's touched it. It's very well preserved. In fact, you go in the door, you see this. I don't know if anyone recognizes what that is. That's 100-year-old seals that were left there on the door. So it's kind of fun to see that. When we were at Scott's hut, not this time, but another time, all these penguins were coming in. This was toward the end of the austral summer. And so we thought they were all coming to, these are Adelaide penguins. We thought they were all coming because they were interested in us. And you're not allowed to go and perturb them or visit them. But if they come to you and you're still, it's fine. So they came and they come right up to you, walk right around you. They totally ignored you. What they were interested in is that the icebreaker had finally made it in. And so imagine a penguin, what that icebreaker must be to a penguin. It brings the water to them from, 30 miles out or something. Thousands of penguins came to the icebreaker. Anyway, that's McMurdo. You fly then to the South Pole in a LC-130 Hercules, ski-equipped. the big skis that they land on. This is still on the sea ice. Fly over the trans-Antarctic mountains, which are really quite beautiful. All looking through these little windows, these incredible, just absolutely incredible glaciers coming down. And then the ride gets kind of, you're excited, but the scenery changes, and it's just flat. It's just flat. You're up on the Antarctic plateau, and I don't know how well you can see this. It's just flat. You see this kind of sastrugi down here. This is groomed for a skiway for the planes. This is a little building, which you'll see close, where you already have. That's where the telescope is, and there's one building, big building here. That's the station. It's a single big building with some underground stuff. So you land there. Immediately they bring out this hose, and you might think that's to fuel the plane, but it's quite the opposite. Every plane comes in filled to the brim with fuel, right? In fact, they bring it to its maximum airlift capability with fuel, and then they take the fuel off, so it has just enough to get home. And the station runs on jet fuel. The generators, everything runs on jet fuel. And in fact, you have to have the equivalent of about 200 of these planes a year in this 3-month austral summer season to deliver the fuel. So at the other end of the airplane is where our cargo goes. And everything for this big telescope, right, the 6.5, 7-story telescope, has to fit in this roughly 9-foot square door and under 25,000 pounds. So we had about 30 flights to get the telescope down there. We walk into there's the station, and so we sleep, we eat, everything's in there, but we walk out about 1 kilometer to the South Pole. The station actually is 100 feet in front of the South Pole now. Next year it'll be about 120 feet. South Pole and all this ice, it turns out, is moving. It's a glacier. It moves about 8 meters a year. So even this, where we're putting our telescope is moving 8 meters a year. Anyway, this looks like we're up ice fishing. That's not the case. You dig a big hole, pack it down, and sinter. You have to build a big foundation to put your telescope on, or it's just going to sink into the snow. Remember that snow layer is 2 miles thick. So years ahead, you start this and pack it down. Then you build these pontoons and brace it, essentially to float your telescope, and then a steel structure. And then the telescope, which would normally just sit on a concrete pad, is going to sit up here and have warm access into our building. While that's going on, the postdocs and I were building the backup structure. This is very high-tech carbon fiber reinforced epoxy, so it's very light. You can tip this thing up, at any angle, and it won't distort from gravity. Very stiff, and furthermore, it has almost 0 coefficient of thermal expansion. It's sitting there on what I'm told is the largest ever machined piece of Invar, 26,000 pounds of Invar, which is kind of a chrome metal that matches the thermal expansion, and that's the backup. It looks nice and sunny there, but I got a close-up of our postdoc, Tom Crawford, just to give you a sense. While we're doing that work, it's about 50 below. It's just very sunny. So any of your skin that's exposed, there's 2 things that happen. You get sunburned and frostbite. So, you keep warm. They give you very good clothes. We have to put on the surface on this. We have 220 panels. They're about a few microns accurate. Each panel has 8 adjusters, and we have to set the whole thing to a parabola in this 40 to 50 below weather. And then you can see the telescope and the steel work. One thing I'd like to point out is you would never, if you could avoid it, put these things together by bolts. But this has to be very strong, and if it was one assembly all welded, it wouldn't fit in a plane. It'd be too heavy. So we have these great big 37 millimeter bolts. And if you grab one of those bolts with your hand, you're going to stick to it. So you're working in your glove, and it turns out just the bolts, 5,000 bolts, 5,182 to be exact, the weight of those bolts and nuts is a plane load. That's that. And so welding would have been great. There's all internal flanges to make it stiff. You can see the truss going together. This reminds me of Wayne's first light. And then this is the day that the whole station, in the summertime, their summer, our winter, about 200 people, they all come out when there's lifts like this. And you say, yeah, it's exciting. They said, well, we just, if you guys dropped it, we wouldn't want to miss that. You know, that would be an event. You know, we would never forgive ourselves if we missed that one. But it didn't drop it. We got it working, and there's a picture of the telescope. I'll show you another. This is that room underneath it, and this is a rotating roof, so that is open to the room, and we can get in, encoders, everything that moves, we keep warm. And we've learned that. We learned that the hard way. Everything that moves that's cold will fail. And not only that, it'll fail in a way that you hadn't thought about. So you can keep learning new lessons every year, or you can get smart and keep things warm. This is, it's hard to see exactly what it is, but our secondary is cold. It's at 10 Kelvin. That's the mirror that's up here. And this is our receiver package. So that's like, you know, a great big camera. And that's, you know, we actively cool that to minus 459. So the most important people in this whole project are our people. So we build this, we have about 3 months, right around Valentine's Day. The weather starts plummeting, gets to about 50 C below or 60 Fahrenheit below zero. And that's it, they call it, last flight out. The station would be closed off. And of course, we managed to get first flight. I don't have first flight picture, we managed to get first flight. And then every year we leave 2 people. They know who they are ahead of time, don't. And they're there, they take the next flight out, and that next flight is the end of October or November. They're there for 9 months, through a 6-month black, dark winter, where the average temperature is about minus 80. So you would think they're crazy. Well, they have to pass a psych test, but I don't know yet if that's to make sure they're crazy enough or they're not crazy. This guy, I want to point out, Dana, you know, he did it in 2008. He really liked it. He came back, he did it again in 2010. He did it with a graduate student, Daniel, here, and convinced Daniel to do 2 years back to back. And then Dana has called me recently and said he'd like to do it next year, too. So, you know, he's really good, so I'm happy, but I worry about him a little bit. So we put it all together, we have our camera, we start scanning the skies, and I'm going to speed things up now through 4 years and show you what we did. So we have 3 bands, and this is the whole, you know, the whole sky around us, shown on a sphere, with WMAP. WMAP is a satellite which mapped the whole sky at about the resolution that DAISY did. But with this telescope, we have a factor of more than an order of magnitude linear resolution, or our size of the patch of the sky we can see is about 200 times smaller. And we need that to look for this subtle effect. This is a piece of the sky then that we image in one of our bands. We have 3 bands. And what you see here, all this slightly more intense or less intense, that's not noise. That is the early universe you're looking at. But that's 2,500 square degrees. There are more pixels here than you can fit on the screen, so you can't see the small scale stuff. I'm going to zoom in by a factor of 50. Right, so take a piece. And so here we are, we're zoomed in, and now you can see there's some, you know, first off, you see this kind of wavy-like stuff. That's very interesting. And I'll show you when we do that trick where we you know, say how much long wavelengths to short. Let's do that for this map, right? Much higher resolution. And that's what it looks like. This is what you saw before. So there's this tone. That tone tells us that you know, that the universe was flat. There's the overtone, the next, 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 and you can tell me whether you still see them or not. The universe is ringing. This is looking at the patterns of sound in the early universe, and it's this wonderful harmonic series. It's just you know, I know you're saying it was just another plot. That doesn't make any sense to me. I never get tired of looking at this. This line is a prediction for what you should see from a model of the universe from inflation, right? And that's it. And you say, well, it doesn't fit out here. Well, that's because now we're starting to see effects like the ones I told you about, where things in the foreground are causing things. So that's actually very exciting. So anyway, I know you're not going to get a lot out of this, but you know, I'm enjoying this moment again, right? This is an angular scale. It's an angular scale. So this is power on the sky, not in sound, but in wavelengths. So these are very long wavelengths on the sky, and these are short wavelengths. If you wanted to say how fast would that oscillate, this first one would be 1 over about 400,000 years. And then the harmonic, 1 over 2, 1 over 1. So very, very long. But that's one way to look at it, yes. So what about this? One thing I want to point out before I talk about this. We knew and expected to see a bunch of these kind of bright little spots. Those are black holes, which sound real exciting, but we've known about them. They emit copious radio and microwave emission. So we expected them. In fact, we knew we had to compensate for them, not let them screw up our results. What we didn't know is that some of them had the complete wrong spectrum to be that. And in fact, what they are is they're very distant, very luminous, some of the first galaxies to form in the universe. And what we're seeing is emission from all the stars forming, not from black holes. And so it's a new discovery, and a whole group of people are doing nothing but following up those type of objects now. But so that's a talk in itself. But what about this effect, right? So, this thing we're looking for. Can we find, between us and looking to the cosmic microwave, can we find all the galaxy clusters? Well, that's what we have to do to test dark energy. So remember what we're going to see. If we look at the cosmic microwave background with our telescope's much nicer. This is like a satellite dish. We have a nice telescope. But if you look at it, what we expect to see is a hole, a shadow. And in this map, there's a bunch of them. Right? There's one there, there's one here, there's one here. So, you thought I was a little crazy liking that wiggly curve. I like this even more. This is finding against the radiation from the Big Bang, against the sphere that surrounds us all, finding all the massive galaxy clusters that are between us. Every one in the observable universe we're finding, right? So it's these guys. We're finding them. And we find them independent of how far away they are. They're just as easy to find them anywhere. And we now have a technique and it works. So this was the first time when they were ever discovered a galaxy cluster using this technique. And it was big news, right? All the science newspapers picked it up, but especially at the South Pole, it was very big news. And parties, we were very, very happy. And then we did our whole survey, and getting near to the end, I love these, monster galaxy clusters found. I mean, they're just enormous. People didn't even know if they'd be out there. In fact, some models would predict you wouldn't find them. And so this is one plot. I'm sorry for all these plots. Here is just the mass, so just a way to rank how big these things are we're seeing versus look-back time. And so all these crosses, each one represents a new galaxy cluster we discovered. And you see we're finding them to very far back, right? We can see when they formed and how many more they're forming. This is about a quarter of our data, right? So we'll get about 4 or 5 times as much as this. And you can see these other surveys using X-ray or other experiments. They look a little farther. Everything gets so much dimmer, and they just can't see. They can't see this stuff. It's too dim. But our technique, we find them. So it's all working. We're finding these things. We are honing in on dark energy. We really now can test it. And especially through that harmonic series, we're finding all sorts of other things. We actually have hints, I would not call it evidence, but hints of other new physics. And one of them is that there might be other neutrinos, more particles than we thought. The mass of those, we're learning about neutrinos. And then actually seeded funding from the Kavli Foundation, we have built now and put down a new polarization sensitive. That's a whole new talk. Receiver, which is going to allow us to look for not just these black spots, it'll do better even on that, but to look for gravitational waves from the universe. So we recently just did the first analysis. In fact, I gave talks at the university earlier this week. But the bottom line, and you can't read it, is that it looks like Einstein's right. It looks like a cosmological constant. Our precision, the one parameter he predicts, it has to do with the property of dark energy. It's consistent with what we measure, and we have precision now of about 5%. So it looks like Einstein somehow managed to get it right. The supernova, our data, all is fitting, but it's too early days. We're going to finish the data, we'll find out how precise it is. And we're seeing hints of all this other very interesting stuff. And it's often true. In fact, it always seems to be true. Every time you make a new measurement, take a lot of new stuff and really get precision information. You answered the question you set out to answer, and then you get 2 or 3 more questions, which seem even more interesting. That's where we are. So let me show you a few parting shots. If you're going to run an experiment at the South Pole and you're going to have a winter over, buy them good cameras, because the aurora, the pictures they take are spectacular. So this is just a couple. In the middle of the winter when the sun is really down below the horizon, it's always green. But these are swirling. They send videos. It's spectacular. When the sun's up a little more, you start to get some other colors in. I think they're just great. Anyway, I'll end there, and thank you very much. I'm told we're a little late, but if there's 1 or 2 questions, we could do that. Yes? What wavelength are you looking at? We're at, what wavelength of light are we looking at? And the wavelength is that we have 3 bands, 3 millimeters, 2 millimeters, 1.4 millimeters. And each one is a fractional bandwidth about 30%. Yeah. Any other quick questions? Yes? To make it steady. Yes. Yes. Yeah, so the question, or the comment, I should say, is that Einstein put in his fudge factor to make a static universe. And that's correct. And Hubble, who measured that the universe is actually expanding, threw that out. And Einstein referred to then that constant as his biggest blunder. He could have predicted the universe was expanding 8 years before it was measured. Actually, 17 years before it was measured. Yes. Okay. Tommaso is telling us we need to go up. I'm happy, if people would like to come up and ask questions, I'm happy to answer them.
Well, thank you very much for coming. It's been a wonderful evening. Let's thank John again. And thank you very much.
Okay. Thank you very much.